Alright, continuing. So to achieve a low entropy state required by living organisms, the overall entropy of the surrounding must increase enough so that the overall entropy is increasing. So here we have a picture showing you a disordered collection of molecules over here. Then you can see by ordering the cell here, by creating this ordered system, heat is going to be released, and overall, the surrounding will become more disordered. So you have increased ordered within, increased disordered without, and overall, you're increasing disorder. So this is how order is achieved, by disordering the system even more while achieving order within a specific area. So at the level of the cell, each individual reaction must undergo the same type of accounting. A reaction which decreases entropy must be coupled to another reaction which will increase entropy. The additive effect must lead to an overall increase in entropy, else nothing will happen. So coupling, we're starting to talk about coupling here. And if the additive effect does not increase entropy overall, nothing will happen. So if two reactions are coupled to each other, for example, or two processes, it doesn't have to be two reactions. It could be a chemical reaction, physical reaction. You could have a chemical reaction coupled to a physical reaction, or a physical reaction coupled to a chemical reaction, or two chemical reactions coupled to each other, etc. But overall, if one is decreasing entropy, the other one has to increase entropy even more. So when you add them up, overall, you're increasing entropy. And we had an example of this in the previous video, so I'm not going to go over it again because we're going to get a little bit deeper and these things are going to be explained a little bit better as we move on. So the change in free energy, delta G. A reaction, whether physical or chemical, has an initial state and a final state. The reaction's progress can be shown as such. So let's take a look. Let's say that we have a reaction, A goes to B, a chemical reaction, and we can say that, well, A is the initial state and B is the final state. Now, how would this look? So if I draw the reaction progress graph, the x-axis will be the reaction progress, and the y-axis will be energy. Then the initial state could be somewhere here, for example. So this would be A, and the final state could be somewhere here, and this would be B. The energy difference between the initial and final state is called the change in free energy, or delta G. So when we're looking at it here, the difference between the energy level of A and B will be called delta G. Because biological systems operate at constant temperature, pressure, and in an aqueous environment, delta G is a direct measure of the change in entropy. Important. If delta G is less than 0, entropy is increasing and the reaction will favor the forward process. If delta G is greater than 0, entropy is decreasing and the reaction will favor the forward process. What do we mean by less than 0 and greater than 0? Let's go back up. So delta G will be the difference in the energy level of the final state minus the initial state. So let's write that out. Delta G equals to energy level of the final state minus the energy level of the initial state. Now you can see that in this case, the case right here, for the picture that we've drawn, B is a smaller number than A because B is at a lower level. So if I subtract a bigger number from a smaller number, I'm going to get a negative delta G. So this delta G here is going to be less than 0. This guy right here is going to be less than 0. This process, A goes to B, actually increases entropy because the delta G is less than 0. And typically this is called an exothermic reaction. But since it is decreasing entropy, it does favor making B from A. It favors the forward process of A going to B. Now, what about if delta G is greater than 0? So let's go ahead and draw that out too. Instead of A going to B, we're going to go B going to A, which is the opposite of what we just did, right? We're looking at the reaction from a different perspective. Instead of A going to B, we're going to look at it as B going to A. And here's our reaction progress diagram. So now, B is my initial state, and B is going to be down here. Exactly where it was in the other one, except now we're flipping the picture, right? And A would be over here. So, B, A. So now when I subtract the initial state from the final state, I get a delta G. So let's go ahead and see what our delta G is. Here's my delta G, and my delta G will be greater than 0. Why? Because the final state is the energy level of A. So delta G. So you can see that A is a bigger number and you're subtracting the energy level of B, which is a smaller number. So this delta G would be bigger than 0. So this process right here, B going to A, actually decreases entropy. So you're decreasing entropy in this case. So this reaction actually does not favor B going to A. This reaction will not actually happen in this direction. It favors the opposite direction, A going to B, because A going to B has a negative delta G. And that's basically what we covered, because the favorability of a reaction is dependent in the direction the reaction is being viewed. So in our example above, when we looked at A goes to B, we had a delta G that is less than 0. But when we looked at B going to A, we have a delta G that actually equals to the delta G above, but has a different sign. So this delta G is greater than 0. I'm going to call it delta G prime because we're saying that they're different, right? But the absolute value of delta G equals to the absolute value of delta G prime. The numbers are the same, but the sign is different. In the case of A goes to B, it's a negative number. In the case of B goes to A, it is a positive number, but the number itself is the same. And we'll stop there and continue later. All right, thank you guys.